All right, so this is the second talk in our series on alignment, and I'm very proud to present Ward Wheeler from the American Museum of Natural History. So Ward has been thinking about the interrelationship between phylogeny and alignment for quite a while. The roots of the dynamic homology approach go back to 1993. So I met Ward last spring while giving a talk at AMNH. So I'd been warned that giving a talk there would be the academic equivalent of sticking my head in the lion's jaws, but it ended up being really nice, and getting to know Ward has been really great. So he's a really sharp mind and is a really nice guy, but I wouldn't suggest trying to convince him of the virtues of hand alignment. All right, Ward, go for it.
Okay, thanks very much, Eric. Hello, everybody I can't see, although I can see some names. So what I want to talk about today is dynamic homology and some of the algorithms that we can use to determine dynamic homologies. And I'm just going to start right in here and hope this works out for everybody. Okay, so this rather wordy slide is an outline of some of the topics that I wanted to cover. So the first of which would be just the goals of phylogenetic analysis, part of which I have to say I was watching Mark Sechard's talk, and I enjoyed it very much, and some of this is a reaction to some of the things he did, or I thought to build on some of the things that he was talking about, to disagree with a few of them perhaps, and agree with a lot of them in reality. So with the goals of phylogenetic analysis, and then static and dynamic homology, how we deal with sequences, some of the issues of how we, very briefly on pairwise string matching, then the tree alignment problem, which is really what we're looking to solve here. Which is NP-hard. So exact solutions, heuristic solutions, and how we can do that in a parsimony minimization context or even in a likelihood context very briefly. How does direct optimization perform by using things like simulations or optimality measures? And then how do these relate to multiple sequence alignment and treating it in essence as an alternate heuristic for the tree alignment problem? Briefly about implied alignment, what that is, and then go on just talk about some example data sets. For example, the Frost et al. Data set that came out in 2006, and then a few of the outstanding issues, at least as I see them, in this sort of analysis that are areas of future research. So before I go on here, I just want to say that the majority of this work, or a lot of this work, in fact, has been done with my colleague Andres Baron at the museum here, so a lot of this work will be drawing on or even stolen from things that he has produced recently. So this is a statement here that Mark mentioned to you, his own personal religion. I hope this isn't quite religious in intensity, but I did want to say some of the things, the way that I view phylogenetic analysis and what the process actually is. And that is that we have data, which are observations of all different diversity of types. We have morphological, anatomical observations, perhaps behavior, sequences, genomic rearrangement events, all sorts of things. And that we want to produce from these data a tree which would include a set of transformations given an optimality criterion. The idea being that we might choose to assess the quality of our tree based on minimization, things like parsimony, weighted or unweighted, or some statistical optimization like likelihood, or we might use an optimality criterion like posterior probability in the sense of maximum a posteriori trees. All of these things, so what we're talking about here are ways to take the whole suite of biological observations and produce trees or cladograms that explain them according to some sort of optimality criterion. And if we deal with implementations, which we all do to test things out and to actually deal with empirical problems, these procedures must scale to thousands of taxa ideally, and certainly tens of thousands of nucleotides with current data sets. Those are the ones that exist today. Now notice I have not said that multiple sequence alignment has anything to do with this process. And the way that I will be treating multiple sequence alignment is as a heuristic procedure that can be used or cannot be used, but it's certainly not intrinsic in any way to the form of analysis. And in this, I definitely agree with what Mark was talking about last month, that multiple sequence alignments are not something we could ever observe or necessarily even need to use. They have no standing in nature, and they might be things that are useful to us, but we have to realize that they're not part of nature itself. So now, just to sort of amplify what I was talking about in terms of the goals of phylogenetic analysis, here's an example of the data set from Xu et al. That came out earlier this year, and it's a series of about 100 taxa, so not that large data set, but there are anatomical features having to do with, in this case, some tarsal characters. You can see up on the left some SEMs, a variety of molecular sources of information, both nuclear and mitochondrial, And we want to incolonate all of this sort of information together into one overall framework. In this case, it was parsimony-based in this study of bugs. So static and dynamic homology, that was one of the main topics here. And so what do I mean by these phrases? And so static homology really would be the kinds of characters that we're normally used to dealing with. Either anatomical features whose correspondences are defined ahead of time, what Mark talked about last time as being homologous, which I would restrict to being putatively homologous perhaps, or primarily homologous, and those features whose, so another example that might be an aligned column in a multiple sequence alignment, and those features that do not have those statements, at least not given to you, and that would be things like unaligned DNA sequences. Now this definition that we're talking about here that I've written down comes from the paper announcing POI that Andres and co-authors, myself included, authored, and the idea that there are different states in characters and that there are correspondences among these states. And in a static homology character, there is a one-to-one correspondence between these states in different creatures, and that one-to-one correspondence is transitive. So if A corresponds to B and B to C, then A also corresponds to C. Now, a dynamic homology character is the complement of this. That is not necessarily the case, and on the figure here, I'll try not to overuse this pointer here. We have an example. We might have three sequences, AA, TTT, TTT, and AAA. We would create three pairwise alignments, let's say, of minimum cost for these. And if we then trace the path of correspondences among the nucleotides, we can see that there are non-transitive paths, that the T's correspond to T's and A's in some cases, but to other bases in others. And so this would be the definition of a dynamic homology situation. We have to do something to decide what to do in order to create a homology or a putative homology scheme. They do not come to us a priori. Now, sequences can be pretty much anything we can linearly array. So they might be nucleotide positions as we have up top, and those of you who work on insects will recognize that as part of the 18S ribosomal DNA from Heteroptera. It includes synaptomorphic Heteroptera. It might be morphological features of a body segment, let's say in some sort of segmented creature like perhaps a vertebrate or even a worm or arthropod head or something like that. Sequences might be calling patterns of behavior. These are some stridulation patterns from crickets. Or it could be a synteny map that you might see on a chromosome, which would include entire loci that would occur in order. All of these are sequences. These sequences compose of alphabets and some common alphabets. We have A, C, G, T nucleotides. Now we also have an indel character, which we will probably treat as an alphabet element, but is technically probably not. In Morse code, you have a small alphabet of dit, da, short gap, middle gap, and long gap. In morphology, you might have elements referring to a body segment like an absence of appendages or antennae or legs or mouth parts. And for mitochondrial loci, you might have a series of loci to have there. And in all cases, you'd have to have an empty string, which would be used to represent an insertion, deletion, or gap character. Now, sequences can undergo a whole variety of transformations. You might have substitutions where X2 and X3 become X2 prime and X3 prime. So in the same place, but they become different elements. You might have insertion deletion events below where you might have element 1 is deleted and element 6 inserted, those sorts of events. Now you can also have higher level events I'm not going to talk about today, such as inversions and moves, which would take chunks of elements or a series of contiguous elements and invert them and move them around. And those are sort of things in the province of rearrangement. I won't talk about it today, but they are basically other forms of sequence transformation. Another thing we have to do is we have to define an objective function. If we're going to talk about these sequences, these distances, we have to define a cost that allow us to identify things that are the same or not the same and to do some sort of minimization procedures. And at the very minimum, these things really should follow the triangle inequality. So that would be that for all x, the distance between any two elements that are identical, x and x should be 0. If x and y are not identical, the distance should be greater than 0. It should be symmetrical, x, y is yx. And observe the triangle inequalities you can see below, that the shortest path, in essence, between any two nucleotides should be shorter rather than going to a third one or third element position. So we have identity, symmetry, and the triangle inequality. Now we're going to talk about tree costs based on an edit distance, and we have to define that ahead of time. There could be different sorts of weighting schemes and all that sort of stuff, but we have to define it ahead of time. Now, briefly, just to bring us all on the same page with pairwise string matching, the idea is that this is a basic technique. If you have two unequal length sequences, or even equal length in reality. And you want to create some object like this that gives us correspondences between the nucleotides in this case. There are a large number of them. Mark talked about this at great length, a very large number of them. In fact, there are more of them for multiple sequences than there are for comparable sized problems of phylogenetic trees. And so the problem is extremely difficult. And the basic technique that we use is dynamic programming when we're talking about pairs or even triplets of sequences. And the basic idea here is that we have a recursion relationship where we're looking at basically the minimum cost between matching two elements, an insertion in one or a deletion in the other. And we calculate these values based on an objective distance function, as I mentioned earlier, which would include then, if we're talking about, let's say, DNA sequences, A, C, G, and T, an insertion or deletion character, a gap. And that we need to put these things together to get the relationships. This can be optimized, but that optimization is entirely dependent on the cost regime one wants to put forward. So for instance, we have two sequences here, ACGT and AGCT, which would look to people who do things by eye. As Eric said, I have to get in a little bit of garbage of people who align sequences by eyes. It's part of my idiom. And so if we had two sequences, ACGT and AGCT, we might say, oh, well, we're smart scientists. We can align those things by hand, no problem. And we can do that, but of course there are different sorts of scenarios. And if we had a scenario where we had the substitutions and indels were equally costly, you would have a cost 2 pairwise alignment right here. If we had the substitutions costing 10 and indels costing 1, we have this thing here, which would also have a cost of 2, which would minimize the number of substitutions. If we make substitutions very high cost over here, then we minimize the substitutions and we have insertion deletion events. And if everything is equal, we get all three of these possible scenarios. So there's no such thing as saying that there is one alignment between any pair of sequences. It depends entirely on the cost regime or the distance function that you specify. Now, what we really talk about in phylogenetics is the larger problem where you have n sequences, and that's the tree alignment problem as defined by Sankoff in 1975. And the basic idea here is that you have a tree with leaf sequences, and one wants to create a series of median sequences such that the overall distance along all the edges is minimized. There's a basic recursion relationship to describe all of these things. It's combinatorially explosive, and this, as with other sorts of either alignment, multiple sequence alignment, like sum of pairs or consensus or tree alignment, are all NP-hard optimizations. So we're not going to have any kind of good solution for non-trivial data sets or optimal solution for non-trivial data sets. And on top of that, there are potentially an exponential number of solutions for any given tree or scenario. So the idea of finding the optimal alignment is as fanciful as finding the optimal tree. So we have to pile that one on top of another when we actually do a real analysis. Now, briefly, there are a couple of exact solutions that one could do which would involve very high dimensional dynamic programming, or in one side, or perhaps even specifying all possible sequences at all the internal nodes. And one could then get an exact solution, but this would only work for very, very small data sets. Again, perhaps for analytical purposes or toy data sets, but would never work for any non-trivial data set. So we have to move to heuristic solutions. So what are the sort of heuristic solutions? And one of the ones that I was involved with very early is the one that we'll talk about a little bit now, which is direct optimization. Originally, it had the name optimization alignment, but I forget even why, but the name got changed in the vernacular about 10 years ago. But the basic idea is this: you do a post-order tree traversal from the leaves down to the root of the tree, and in each case, one does a pairwise alignment of the two descendant sequences, and then creates a median that will represent all the states basically between, or many of the states between the two sequences that are the descendants of that. So you create a median sequence at each case. Now that median can be redundant in some sense. So it can be, if you look at this example down here, the Y, meaning there's a T or a C potentially at that position. Since this median can be redundant, potentially an exponential number of possible medians can be contained in each representation. So it's very compact. And then as that goes down the tree towards the root, one is evaluating a very, very large number of medians, and then this is why the procedure is as effective as it is. One also point to remember is that gap elements, sole gap elements, not those that represent an ambiguity, are removed from all the medians, since gaps cannot occur in real sequences. So it's obviously an n squared kind of operation. On the right, you see some pseudocode that Andres and co-authors have in a paper to describe it more formally. But the idea basically is that you're trying to get a series of median sequences that are real sequences, each one of which covers the distance between the two descendants sequences, and then we remove those gaps and go on down the tree such that the overall operation is minimized. Overall cost, I should say, is minimized. An example, sorry.
Ward, it seems to me like there could be some ambiguity as far as, like, you could have a string of G's and you could have deletions in lots of different places for a given
Absolutely.
median
You don't
sequence.
capture all of the ambiguity. You capture a subset of the ambiguity, absolutely. So the result will be an upper bound, no question about it.
All right, thanks.
So the question is, and we'll try to get to it later on, is how bad is that upper bound? And are there any guaranteed results that we can get for that? But that's a very strong point. All we're doing in representing, as Eric pointed out, is we're basically taking a fixed length and having ambiguities within that fixed length. Now, if one of them is a gap as part of ambiguity, that will imply ambiguity in length, but it's not containing all of the potential medians. It's not like Heinz method where you'd have, for instance, all of the equal cost alignments in the tree graph there. It's a reduced alignment graph in some sense. Now here's just another example of that, just showing how you would actually do that. As Eric pointed out, the top example here exemplifies what Eric was talking about. You have 4 Gs and 3 Gs, I'll put that up here, in the 2 descendant leads. And then we're picking one of those positions, the 4th position, to be potentially ambiguous. So the parentheses represent ambiguity being either a G or no G there, and then we cost that one indel. In this case, if we had indels costing 2 and substitution costing 1, we create that median, and then that median is compared to another descendant taxon down here, another leaf sequence here. This case, we require 2 substitutions. We have another cost of 2, and then another insertion and deletion event here in the 4th position for an overall cost of 6. So the time complexity for evaluating one tree would be n squared in the number of length of the sequences, and k in the number of sequences per tree. During a search, there's a lot of shared information, so it's not as bad. That k factor goes down significantly, and there are other things one can do to reduce the n squared to n log n, or some sort of complexity, how to do with that. Now as I said before, we don't have any guaranteed bound for the behavior of direct optimization. So although it may behave well, we'll look at that later on, we can't really say how well we can guarantee it to behave. But there are other methods that aren't quite as strong in terms of performance that do have guaranteed bounds, such as lifted alignments and uniform lifted alignments of Gusfield and Wang and Gusfield, Wang et al. And in this case, one assigns to the interior vertices one of the descendant leaf or one of the descendant vertices from the previous assignment. So if you look up here, we have, so we assign S0 or S1 to this vertex, S3 over here, S5, S7, and in each case we assign one of the descendant vertices to each case. In the uniform lift, we make a choice of left or right. Now, one of the nice things about this is that this has a guaranteed bound of 2. So we know that however bad a lifted alignment is, it's within a factor of 2 of the best possible, the optimal alignment. And we can use that to get a gauge on how well our other methods are performing. Other possible methods are fixed states. I talked about a number of years ago, which is expanding the potential set of observed leaf sequences that can go to each one of the internal nodes. So it will have the same bounded behavior, but in practice will perform somewhat better because there are more options. And one could expand that out even to an exact search or some heuristically useful subset in a search-based optimization where you look at a heuristically defined set of sequences, and by dynamic programming along the Sankov algorithm, Sankov and Cedergren, one can then evaluate the sequences at each internal sequence to hopefully minimize the overall tree. So these are other heuristic solutions. Sankov and others also point out an iterative improvement, which is often used in implementations where previously we were talking about, for direct optimization, for instance, it's an n squared procedure using only the descendant information. But then one can go back after the trees have been initialized and then do n cubed sorts of optimizations at each node where you look at the 3. For instance, for V2, you look at S0, S1, and V1. Do a 3-dimensional sort of dynamic programming to get a better idea or an exact solution for that particular node given the 3 nodes that are adjacent to it, and then go around the tree and repeatedly examine each element until it's stable. And this sort of iterative refinement or iterative improvement has been shown to be very effective in the past, and is perhaps a less of an improvement on later algorithms, more recent algorithms that Andres has talked about. Now, just briefly, I can say that this can also be done equally well in the likelihood context. And this was published in, I think, 2006, but has been implemented in POI3 for 5 or more years, maybe 6 or 7 years. And in this case, basically, what you do is you just take the log transforms of the probabilities transition between different states. Now, on the upper right, I have a very simple sort of Neyman model, but one can do with a more complex one, where you have 5 states, in this case, AC, GT, and gap. Given a certain edge parameter, one can then calculate the probabilities of transitions between the different states. Then taking the negative log transform of that, one can go back to the same dynamic programming algorithm that was used to do string matching, with one subtle distinction, and that is right down here. So the recursion relationship, instead of choosing the minimum of the paths to get to that cell, so the diagonal path, which denotes a match or mismatch between elements, to an insertion deletion. Now, for a regular string alignment, we took the minimum of that. In this case, we would take the sum to get the overall probability of that statement. Now, this is, now I think last time Mark mentioned the forward-backward algorithm. So if we were to take just the minimum, that would be the Viterbi algorithm. In this case, the same thing. If we take the sum, this would be the forward, in this case, the forward part of the forward-backward algorithm. So that way we can get the overall alignment score given all the possible paths, all the possible alignments that are there. This is, and I said now down here, this can be done for a general model for GTR. This is just an example of how one would do it over here with the log transforms and then a Neyman model with 5 states. There are complexities that come into it though right away, which is if you take the sum of the paths, that is the correct pairwise probability between the 2 sequences. However, that is a collection of all possible alignments in essence between, in fact, between the 2 input sequences. If we're going to represent one potential alignment, look at the dominant path. So this would be, for instance, the Viterbi solution versus the forward-backward sort of solution. That particular dominant path, that dominant median, could represent a very small part of the overall likelihood that one would look at. This phenomenon has been pointed out for a long time. Certainly, Jotunheim has, and Thorne et al. In their models in 91 and 93 did. And here's the simple example we have here. The dominant likelihood would be roughly 1/3 in this case of the total likelihood, meaning all the possible paths. This does present a problem because if you're going to continue down a tree and try to optimize the entire tree, one has to find some way to accommodate all of these different paths if you're going to use the sum approach. If you use just the dominant approach, it's very straightforward. Just take the dominant values. It's just like the regular direct optimization algorithm. If you're going to use the total approach, then, as Eric pointed out, you're not going to contain all the possible alignments or all the possible medians in that solution, so there's going to be sort of a mismatch between the transformation paths that you will pick and the overall probability that you'll actually get. I hope that was reasonably clear. We can come back to it, assuming that what I said was not clear. Now, there are a couple of other points here to be made, which is, as I talked about earlier, we don't have a good idea or provable bounds for direct optimization, but there are polynomial time approximation scheme for the tree alignment problem. And this comes from Wang et al. 2003. And this used a combination of uniform lifted alignments and exact solutions. And the basic take-home message here is, if let's suppose we want a 1.5, a factor of 1.5 bound, the complexity is extremely high. So if there's a factor of the number of sequences, basically the size of the tree, the depth of the tree, or how many levels between the root of the tree and the leaves, how many splitting events there are. And then if n is length of the sequences, this is an n to the 5th algorithm to get a bound of 1.5. So as Mark said before, always do linear, usually do quadratic. When you get to a third cubic equation, you really have to wonder whether it's worth the effort. And this is even worse than that. So getting a guaranteed bound of 1.5 is a very tough process. Now, this is some work that Andres Veron has done to look at the behavior of the performance in empirical, in simulated cases, but in actual operation, what direct optimization is doing. And I hope you can see these over here, but these are a number of, this is a simulation study, which I'm not a real fan of, and I'll talk about that later on in a while, but to get an overall idea of the behavior of your method when you really don't have any bounded results, simulations do offer you an alpha level idea of what your behavior is. And so what Andres did here is he actually looked at simulated data and then fixed states, we talked about before, which was a lifted alignment with all possible leaf taxa assignable to an internal vertex. And then affine DO and affine DO plus iterative. So that's an affine gap model version of the direct optimization algorithm that Andres has done for part of his thesis. For our arguments here, we can talk about it in this context as equivalent to DO. So we have DO and then the iterative improvement on top of direct optimization. And so if we look at this table over here, one of the things you can see right away is that the simulated data are basically never optimal. That's one thing we can say. So the true path is never the optimal path, or for non-trivial data sets, certainly. Now that means that the truth factor we can't use. Perhaps you can zoom in the PDF. Sure. I got a request to Eric to zoom in on the PDF. So you know what am I going to do here? Eric, do I make my window just smaller on it or something like that?
I mean, I don't know exactly what you're using to look
I'm
at it,
looking
but
at this.
are you are you using
Keynote.
Keynote? Okay, sorry. I thought maybe you're using a PDF, in which case you could just zoom in. I'm not
Let me see
sure.
if I can be smart here for a second and blow this up. I will zoom in. Aha.
Ah, that's already much better. Yeah, okay.
Now, let me get this over here. Okay, and we're talking here. Okay? So, if we look at simulated, the first in each of these boxes, simulated, fixed states, affine DO, and affine DO plus iterative. Now, the key thing is the simulated is the true path. That's what actually happened in simulated data. Fixed states is a guaranteed factor of 2 in the worst case over the absolute minimum. And then we have affine DO and affine DO plus iterative. Now, affine DO plus iterative means we did the n squared process to get the initial assignments, and then we did an n cubed process to try to refine them. And so these are the ratios that we get of the solution, the minimum solution, median solution, and maximum solution over a different number of random addition sequences and other sorts of things like that, compared to the minimum that's possible based on the fixed, the lifted alignment minimum, and LP in some case, linear programming minima. So what you can see is basically that in every case, the true values are not optimal. And that the fixed states would be the worst in this case, significantly above it, except in some cases we have large things. And then we have affine DO, which is within 5 to 10% in most cases. And the iterative improvement does not improve that much on it, it does in some cases, until you get to very long branches. Now that's the branch length is the mu-t component of the likelihood analysis, so 0.3 would be very large. So as you get to larger branches, the algorithm gets down to, let's say, within 30% or 40%. Up towards 50% even. Now, if we look at these graphs on the bottom here, we have the distribution of for branch length that are very short, 0.05, 0.1 intermediate lengths, and 0.3 longer branch lengths. And then we have the approximations of the affine DO or direct optimization. And you can see that for the short branches, we're very tight. We're down around 10%, 15%. And then for intermediate, we're about 20, 25%. And get to 40 to 50% for very long branches. And that, what I want to bring you back to is remember that was to get that level of behavior in a guaranteed sense required an n to the 5th algorithm, whereas DO is an n squared algorithm. So we're getting between 10% and 30% of the optimal solution in an n squared context. Now, Eric, I'm going to go back to what I had before, the original view, if that's okay. So the take-home message here is a comparison with known simulated data within 10% in short branches, 30% on long branches. Now that's one use of looking at performance, but in reality, we can never use that for any empirical data set because we can never know the true solution in any real case. And in simulated data, the true solution is not optimal, and the optimal solution is not true. So the truth value, though it helps us get some sort of intuition as to how well things are behaving at a very alpha level sense, the reality is all that actually matters is the comparison of the optimality of the algorithm we're using and their implementations. So for real data, we want to see is how well are things behaving. Now here's a small example down here. These are some data, some frog data from Julian Pavlovich. And this actually is comparing POI3 versus POI4, which is POI4 is a complete rewrite in the last few years of the POI software. And that data set had a typical sort of data set. It was roughly 100 taxa. There were morphological characters. There were 9 different molecular loci. And so we can see here how well our new algorithm has performed compared to our old algorithm. It's roughly 1,000 times more effective. And the way we say that is by looking at the quality of the trees that come out. In this case, parsimony. So what were the parsimony scores? And to get a parsimony score of the same quality with POI4 as POI3 would require roughly 1,000 times more work. So like comparing optimality, straight optimality, irrespective of, we don't have to know what the true solution is, what the optimal solution is, I should say, but we can still say that the newer algorithms are more effective than the older algorithms. Now we can extend this to looking at multiple sequence alignment. So the question I would say is, well, multiple sequence alignment is fine, but we really need to know how effective it is both in time and optimality values. So we don't know what the real answers are, but we can still apply multiple sequence alignment techniques and then compare them to direct optimization techniques, at least in the guise of POI, and see how effective they are. And so here's a small comparison of 4 different data sets. We have a MANTID data set from Mike Whiting et al., which has 62 taxa. They're 18S data, so roughly 1,800, 1,900 line positions, 500 of which were variable. And then a metazoan data set, which with 208 taxa, an archaeal data set with 585, this is a small ribosomal subunit of 185 taxa, and a mitochondrial data set of roughly 1,000 taxa. So in each case, I did several things. For POI, I did, well, for the muscle and clustal analyses, I aligned them via the two software packages, and then took TNT, fed them back into TNT, and by Golubov et al., and did 2 searches on them. One was a very simple, quick search, mult, just a bunch of, I think it's 10 random addition sequences and some TBR branch swapping, and then did a very aggressive search that had all sorts of higher level heuristics, genetic algorithm things like tree fusing, simulated annealing things like tree drifting, the ratchet, all sorts of very high-powered analyses. And then for POI, all I did was 1 n-squared build, 1 random addition sequence. So I did the worst possible heuristic one could ever do with that piece of software. And then we compare the lengths of the trees we get out of them. So now I should say ahead of time, I'm not a very experienced muscle user. This is probably a little unfair to muscle, and I will improve these values. So I think muscle would do a little better than what it actually says here. But in both the cases of muscle and clustal, you can see that looking at this next to last and last column, that for the first data set, we get 1,044 or 1,037. For 1,044 steps, that has TNT on muscle using gaps as characters, I say also. So all the gap information, the indel information is left in as is and used as character, and all of them are weighted equally. We can't use any heuristic, we can't use any affine gap cost because we can't do that with normal phylogenetic software. We can't do that with things like TNT and POB. So if we look at the muscle clustal data set for the analyses of mantids, we see 1,044, 1,037, and the POI cost was 941, or 981 if we use the implied alignment. Now we see the same pattern going on here. So we look at, let's say, the metazoan data set, we get 35,000 steps for the muscle alignment, 29,000 steps for clustal, and 27,000 steps for POI. Then we get 40,000 for archaea, roughly 40,000 for archaea again for clustal, 38,000 for POI, and then for the mitochondrial data set, 128,000 for muscle, 115,000 for clustal, and 80,000 for POI. And furthermore, if we actually work very hard, so we go from a very small search to a very large search, we get very small improvements of things like 40 or 50 steps in the case of the alignment methods, multiple sequence alignment methods, but they are still more than 30 or 40% more costly than a single random addition sequence using POI and direct optimization. So if we had actually done more aggressive searches, we would have improved on this. And it's n squared, so the single Wagner build of the POI search took roughly as long as the clustal analysis did, within 10% or so. So it's about the same time period doing clustal analysis, but you get a 30 to 40% improvement in the search. And that really is because of the heuristic intensity, the heuristic quality of multiple sequence alignment versus the heuristic quality of looking at a tree alignment directly, or searching for the tree alignment directly. In simulated data, we see the same behavior. This is Ogden and Rosenberg did a very large number of simulations, 15,400 simulations, and they were comparing a two-step analysis of Clustall plus POP versus POI. They compared to POI 3. I used POI 4. And in their case also, the true alignment they tested also was never the optimal solution. And in every single one of these cases, the POI analysis was always more optimal than Clustall plus POP in all the 15,400 cases. Now, what Ogden and Rosenberg, to be fair, were more concerned with was how did the implied alignments that came out of the software, out of POI, compare to the true alignments, which is not a big concern of mine. This was examined by others later on. But my main concern here was what was the quality of the algorithm, so the heuristic. So what is the quality of the optimal solution coming out of it, irrespective of whatever some multiple sequence line might or might not look like. And based on these assumptions, these simulations, we always got a better analysis using POI. This has been shown in other empirical cases. For instance, this is an example. I try to put some organisms in here so we can talk about a little bit of biology occasionally. This is a case of cephalopod work done by Annie Lindgren and Mary Megan Daly at OSU. And there's some pretty cool creatures in here, including the giant squid. If you can see Architeuthis down there. This is the picture from the museum's display of the giant squid of being eaten by a sperm whale that many people are familiar with. Here's Architeuthis down here. What Meg and Annie had done was they compared using a Clustall analysis with TNT and POI for these two different cost regimes. And if you can see down here, the TNT Clustall analysis was 6,129 steps versus 4,111 steps. Sorry, versus 5,066 steps for POI. So we got roughly a 20% improvement using the direct tree alignment, the direct optimization heuristic versus a multiple sequence alignment heuristic. Now, one thing I did want to talk about very briefly is, and I think there was some confusion a little bit last week when if I understood it properly, when Eric and Mark were talking about how does the approach of value phi relate to the approach of POI or direct optimization. And Mark was saying, well, POI creates an alignment, a multiple sequence alignment for every tree, and so since multiple sequence alignments don't actually exist, that seems epistemologically suspect. Well, I think there might have been some confusion here. POI does not, or direct optimization never uses a multiple sequence alignment to evaluate the length of a tree. It doesn't have to do that. It actually looks at just the edges on the tree in a pairwise context, so no multiple sequence alignment is ever created. However, after the analysis, one may create a multiple sequence alignment, which I've just used the word implied alignment to distinguish it from normal multiple sequence alignment, which would contain all the transformations, all the putative homologies among all the leaf elements, and then the implied homologies that occur there. If you take this implied alignment for that given tree in the same cost regime, you return the same tree cost that POI will generate for you. So it's self-consistent in that sense. But this is a post-analysis description, in essence, or a way of looking at what's happening on the tree. That alignment, for instance, has no meaning outside of that tree. It would not be usable really to diagnose anything else or as a search base, although some people have used that. It really is a way to look at what's happening on the tree post facto and really has no role internally in the evaluation of the tree itself. One might use it for heuristic purposes, but in principle has nothing to do with it. And this just shows in a diagrammatic form how the implied alignment actually relates to the tree alignment itself up there. So if we had that tree, we'd see in the upper left, relating those 4 or 5 sequences. In essence, we have a series of correspondences that are implied by that tree based on the median assignments, and you can see here there are 4 of them: the blue, blue, green, pink, and orange if they come clear. And one can see that these lines only connect terminal nucleotides that are available. If there's nothing there, there's just nothing there. They don't correspond to anything. And so then you fill in the ones that have no correspondence with gap elements, and then you get this kind of structure here. So it looks a lot like a multiple sequence alignment. It behaves as, it can be used as one, I suppose, but it does have some other behaviors that make it sort of different. And here's a little cartoon to show this. These are some sequences from chelicerates. And this column shows here 3 A's in 3 different positions that are each in unique columns. And I think most of the time people would look at that and say, oh, that's obviously a misalignment. Excuse me, fix that. And It would be if the group were monophyletic, because that would mean there were one insertion event that generated those A's. If the group is not monophyletic, there are 3 independent insertions of those A's, so they are not in any way homologous and cannot be, and so therefore they appear in 3 different columns. So an alternate tree, where those 3 taxa, Chambria, Mestigoproctus, and Artemia were one group, you would have had 1 column for that tree. So that's how the implied alignment differs from what one would think of a strong one. Yeah, let me do that. So go right ahead. I'm going to zoom in on that position a little bit. And let's do one more just for good measure. So I'm talking about this column right here. So there are 3 aligned positions in the implied alignment, each of which only has 1 nucleotide for 1 taxon. So if one were doing things by hand, we'd say, oh, this is a misalignment, let's just put those guys right together. But in fact, that is a direct outcome of the fact that they are not forming a subtree. If they were forming a subtree in a partition, you get 1 position there. I'm going to zoom back out and continue. Now, I want to sort of just finish up briefly with another exhortation for how we really need to use these techniques. And here's an example analysis. This was Frost et al. 2006, the Amphibian Tree of Life paper, a humongous paper. And this data set, there were 532 terminal taxa, all sorts of amphibians. There were a large number of molecular loci, 8 loci of mitochondrial transfer RNAs, mitochondrial large ribosomal subunit, protein coding like rhodopsin, tyrosinase, histones, 28S, 7th absentia, a large collection. This is a fairly typical sort of data set that you would see nowadays for a fairly comprehensive analysis. Hundreds of taxa, 10 loci or more, in this case up to 5,000 nucleotides in these 10 loci, and hopefully you see some morphological characters also. The broader the taxon, it gets more difficult, but in this case there were some morphological features. And you want to be able to analyze these things in a reasonable set of time. You want to be able to take all the sorts of information and actually be able to look at them in the time, as Mark mentioned last time, until you get bored and you stop, which for most scientists seems to be about a month. So a month on your hardware, that's what most people are willing to do. And so the point here is, I don't know if you've ever seen this paper, but it's actually it's the only centerfold cladogram I've actually ever seen. You actually have to fold it out of the manuscript because it's so large. And this tree over here is an excerpted version of that. And because of the scalability of the procedure, since we were doing n-squared searches on trees, even though that would take some time, we could still do very aggressive searches. So we do random addition sequences, we do tree drifting, again, a form of simulated annealing, ratcheting or perturbation techniques, tree fusing or genetical algorithm sorts of things, even manual arrangements to try and look and see if we perturb the optimum in different sorts of ways. And then all these techniques can be applied because the procedure is relatively efficient on the tree alignment problem, as opposed to being limited in some cases to, let's say, nearest neighbor interchanges or very small tree perturbations because the optimization of the given tree is so expensive. And over here on the right, you see some nice pretty organism pictures from Sicilians in the top to Plethodon salmonids. This one is actually, this taxon's in my backyard in great numbers. And then a variety of frog taxa, so bufonids and hylids and rhonids. So my point really here is that we also want to develop techniques that can be used by biologists to solve real problems, and that does impose constraints on the implementations. Really, they have to be reasonably scalable, and you have to be able to use a diversity of sources of information to make them useful for the community at large. So what are some outstanding? There's just a couple of outstanding issues with DO that are ripe for the picking. The issue, as I said, of multiple medians. If you can do a Bayesian analysis and you want to integrate over a lot of medians, or in principle all medians, one has to have a way to compactly represent and be able to deal with them. And that applies to maximum likelihood also. Not to the same extent as Bayes, of course, but it's the same basic problem. And that's the problem Eric was talking about before. DO represents a subset of the possible medians, but you really, in that case, would want to look at all of them. And not even just all the best ones, but really all of them. So you want to have integrated likelihoods, you have to have integrated medians. The other big issue is guaranteed bounds. We don't have provable bounds, which would be very nice to have. That would also tell us about the technique and hopefully allow us to improve it. Certainly there's great room for improvement. But right now we don't have provable bounds, and there's no really good theoretical framework for that. So just to make a few final points as I'm wrapping up here, and would be that in terms of phylogenetic analysis, I want to argue strongly for optimality-based methods, and that would be parsimony or likelihood or Bayes or other sorts of Bayes, maximally posteriori Bayes but it would not be things like clade posteriors or jackknife trees or bootstrap trees or things like that. The algorithms must be scalable in terms of data size, in terms of length of sequences, but also in terms of numbers of tags. So we have large data sets out there and they're only getting bigger. We need effective algorithms that will allow us to look at a broad variety of information. Direct optimization has a lot of these properties. I would argue that multiple sequence alignment is not a very good heuristic. When we talk about effective algorithm, I mean, how good is the quality of the solution? I think in head-to-head analyses, even given the same amount of time, the multiple sequence alignment algorithms, as implemented in several pieces of commonly used software, are not as effective as those that are implemented in other pieces of software that are using tree alignment problems. And I suspect that will be the case broadly as other tree alignment algorithms come out, that tree alignment approaches like direct optimization will be more effective in general than multiple sequence alignment. And the last is that, as really an implementation issue, is that implementations must be able to use diversity of existing data types so that biologists can solve real problems with them. And with that, I want to acknowledge a number of funding agencies like the U.S. National Science Foundation, the Tree of Life Program especially, NASA, National Aerospace Space Administration, is funding some of the work here, DARPA, funding some of the work as we apply to viruses in the American Natural History, and very much to Eric Mattson for really doing a huge amount of work and creating this wonderful international seminar series, which I really appreciate very much. So thank you, everybody, if there is anybody who's paying attention at this point, and I'd be happy to try to answer any questions I can.